Today we're going to begin our discussion of gases and how gases react and the properties of gases whenever they are in a closed container. One of the first things we want to discuss when we think about gases inside a closed container is the pressure that gas exerts. When we talk about gas pressure, we are talking about the pressure that a gas creates due to the collisions of the gas particles with the walls of the container. When those gas particles collide with those walls, it creates pressure. And the more collisions we have, the more pressure. So that's a key statement. More collisions with the walls of the container. Again, it's with the walls of the container equals more pressure. One of the things I usually ask my students to do is to imagine that this container here is like a demolition derby arena. And all these little particles inside here are all those trucks and cars and things that are participating in that demolition derby. And if we think about what those are doing, it makes it really easy to conceptualize what's going on when we change the conditions of the gas in the container. For instance, what would be the effect of adding more gas to the container? So in our analogy, adding more gas would be the equivalent of adding more trucks or vehicles into that demolition derby. Think about what that would do to the pressure. Hopefully you realize that the pressure would go up, the pressure would increase, and the reason it would increase is because since there are more particles, more gas particles, there are going to be more collisions with the walls of the container and therefore a higher pressure. Again, I can't emphasize enough, we're talking about collisions with the walls of the container. So now think about how increasing the size of the container, how that would affect the pressure. So think about our demolition derby and imagine increasing that arena size. What would happen to those collisions? Hopefully you realize that there would be fewer collisions. And since there are fewer collisions, our pressure is going to, decrease. So the pressure is going to go down. The next one, increasing the temperature of the container. How would that affect the pressure? Think about what that does to the particles. If you increase the temperature, you're going to speed up those particles. And if you speed up the particles, there are going to be more collisions. More collisions, more pressure. So you are going to increase the pressure, and again, the particles move faster, so there are more collisions. More collisions with the walls of the container. Hopefully I've said that enough now. Now when we measure pressure, we measure it in these units. Millimeters of mercury, abbreviated mmHg, atmospheres, abbreviated ATM, and I don't know how many times I have people call that atoms. It is not an atom, it's an atmosphere. Torr, no abbreviation that I know of, and kilopascals. KPA for the abbreviation for that. So those are the 4 different units that we can measure pressure in, and fortunately or unfortunately there are lots of ways those different units are used in science. I would say that kilopascals is probably more often used in physics, but you'll see millimeters of mercury, atmosphere, torr, kilopascals, all of those used. So we need to know how all of those are related. Now at sea level, air pressure is equal to 1 atmosphere. And the relationship of atmospheres with millimeters of mercury, torr, and kilopascals are related here. An atmosphere is equal to 760 millimeters of mercury, which is also equal to 760 torr, which is equal to 101.3 kilopascals. And we can use any 2 of these and create a conversion factor. For instance, we can say that for every 1 atmosphere, there are 760 millimeters of mercury. We can say that if there's 760 torr, that we have 101.3 kilopascals. We can say that if we have 1 atmosphere, we have 101.3 kilopascals. So depending on the situation and what we're dealing with, we can use, again, any two of those terms and create a conversion factor out of it. Now, right here you see a barometer, just kind of a classic barometer, and up in this area up here, we have a vacuum. This particular barometer is showing that it's being measured in inches, usually of mercury, sometimes of water, but in this case it's mercury. And an open container down here at the bottom, and as air pressure pushes down on that liquid in that container, it pushes the liquid up the tube, and the higher the air pressure, the higher the mercury in the tube, and that's how we measure, that's one way of measuring the atmospheric pressure. Now, if we want to convert from one unit of pressure to another, we've already shown that we can use those conversion factors, those terms on the previous page, as conversion factors. So let's say we want to convert 895 millimeters of mercury to torr. If you look back on the previous page, you already saw that 760 millimeters of mercury was equal to 760 torr. They are the same thing. I do not require you to show any kind of work if you're converting back and forth between millimeters of mercury and torr. You can simply say, in this case, for instance, that 895 millimeters of mercury is the same thing as 895 torr. If, however, we want to convert 895 millimeters of mercury to atmospheres, then we need to use the conversion factors. So 895 millimeters of mercury, and if you look back on the previous page, you'll see that it said that there were 760 millimeters of mercury for every 1 atmosphere. So that's a conversion factor that we can use. We need for millimeters of mercury to be on the bottom. So the 760 millimeters of mercury is going to go on the bottom, the 1 atmosphere on top. And since the 760 millimeters of mercury is an exact number, meaning it has an infinite number of zeros after it, we are going to find that this now has 3 sig figs. The 895 gives us 3 sig figs, since we're not going to count the 760 millimeters of mercury. So when we divide this to 3 sig figs, we end up with 1.18 atmospheres. And on your worksheet, that's the first thing you're going to do, is up at the top, you're going to be finding those different conversions between the different measurement systems for pressure. So make sure on any of them that are going between 2 non-equal units, other than millimeters of mercury and torr, you're going to need to show this setup. So make sure you do all of that. If you don't show that, you're going to lose points. Now, Dalton's law of partial pressures simply states that if we have a mixture of gases inside a container, the total pressure of that container is going to be equal to something called, using something called the partial pressure, it's going to be equal to the sum of all the partial pressures of each gas that's in there. Now, what does that mean? It means if we had 3 gases in there and each one of them exerted 1 atmosphere, so each of those had a partial pressure of 1 atmosphere, Dalton's law says that we can get the total pressure by simply adding those up. And the total pressure of that container would be 3 atmospheres. That's really all the law says. So take, for example, this first one. It says determine the total pressure in millimeters of mercury, torr, and kilopascals of a mixture that contains oxygen, nitrogen, and helium if the partial pressures of the gases are as follows. And it gives us this information. So the first thing we want to do is to set up our equation. We know that the total pressure of the system, we're going to call that P sub T. The total pressure is going to be equal to the partial pressures of all of the gases in this container. And in the case of this particular container, we've got oxygen, we've got nitrogen, and we've got helium. Notice that helium does not have a 2. It's not one of our diatomic gases. Oxygen and nitrogen both are. So to get the total pressure, we're going to add up the 150 millimeters of mercury for oxygen, 350 millimeters of mercury for nitrogen, and the 200 millimeters of mercury for helium. And when we add those together, we end up with 700 millimeters of mercury. Remember the rule for adding and subtracting. When you add or subtract, we don't use the normal sig figs. We use places past the decimal. Since all of these values have 0 places past the decimal, then our answer should have 0 places past the decimal. So 700 is the correct sig figs for that. Now don't forget that it also asked us to do this in torr and kilopascals. We've already established that torr is easy if we have millimeters of mercury, because torr will be exactly the same as millimeters of mercury. So 700 torr, boxing that in, 700 torr will be the value for pressure in torr. But now kilopascals we're not going to need to convert. So let's take that 700 millimeters of mercury, and if you remember from the, or look back at the previous page, I don't expect you to have this memorized yet, but there are 101.3 kilopascals for every 760 millimeters of mercury. Since millimeters of mercury needs to be on bottom to cancel, then we can use that conversion factor just as it is. So the 760 millimeters of mercury on bottom, the 101.3 kilopascals on top. And when we take 700 times 101.3 divided by 760, we end up with 93.3. And since millimeters of mercury cancel, 93.3 kilopascals. Now, remember, now we're multiplying, dividing, so we're back to using our normal sig figs. And if you look at the values here, the one that's going to determine sig figs is the 700. Since there are zeros at the end and there's no decimal showing, then we only want one sig fig in our answer. Now during this unit, I'm going to actually ask that you not put values in scientific notation, which you might think, yay, but we're so used to scientific notation now that we have to really think about what our answer is going to be. And if we want only one sig fig in this answer, then we're going to draw our line at the one sig fig, but we have to make sure that we keep both of our place values up to the decimal. So the answer is going to be 90 kilopascals. So that's the answer to that question. Now, the last thing we're going to talk about, we're not actually going to get to do a lab using this year, but if you take AP, we will be next year. And that's what we do when we collect the gas over water. When we collect the gas, and we can just imagine some container over here that a chemical reaction is occurring in, and it's giving off a gas, and it's being collected in this water, in this bottle. As the gas collects up here, it's going to force the water out. And so we're going to have this this gas collected over water. Now, let's say that the gas we're producing is hydrogen. So over here, we're producing hydrogen gas, and it's going through this tube and going into this container. The one thing we have to remember is that inside that container, we have not only hydrogen gas, but we also have water vapor. And that's really important, because when we do calculations with this, we have to make sure that we are dealing with just what we call the dry gas. In this case, it would be just the hydrogen. And I would want to be able to subtract off that water vapor from the total pressure in order to get what the pressure just hydrogen is. So out here, I've got some kind of barometer out here that's measuring this pressure right here that's being exerted from the atmosphere. Our barometer is a disc shape, and it actually gives the values in centimeters of mercury, which is kind of confusing, and we have to convert for that. But it calculates the pressure. Now, the thing is, there's only one time where the pressure inside the container and outside the container are the same, and that's when the level of water inside and outside the container is the same. So when we collect a gas, one of the things that we have to do is to make sure and measure the volume that's in that container when the water levels are the same, because if we move that bottle up or down any, it's going to change the pressure inside that container. So what does that mean? Let's say we're doing a lab, and it says the student collects the gas over water at a temperature of 24 degrees Celsius. The atmospheric pressure of the room is measured on the barometer, and it's 77.1 centimeters of mercury. After the water levels inside and outside are the same, like we just showed, the gas containers equalized, what would be the pressure of the dry gas that she collected? So the first thing we want to do is to look at this equation up here. It says that the atmospheric pressure, the total pressure, is going to be equal to the pressure of the dry gas plus the pressure of the water vapor. And it already said that the pressure of the atmospheric pressure measured on the barometer was 77.1 centimeters of mercury. We don't measure in centimeters of mercury, we measure in millimeters of mercury. So the millimeters of mercury would be 771 millimeters of mercury. So there's our atmospheric pressure, 771, not atmospheres, sorry. That would be a heck of a lot of pressure. 771 millimeters of mercury. We're trying to find the dry gas. That's our question up here. So P dry is what we're trying to find. And we need the pressure of water. Now, water vapor pressure changes as the temperature changes. It very specifically told us it was at 24 degrees Celsius, so how are we going to know what the pressure of water is? Well, they very nicely give us some tables. And we can look up water vapor pressure by looking on a water vapor pressure table. And as you notice, the pressure increases as the temperature gets higher and higher. So we look for our temperature, which is 24 degrees, and we see that the water vapor pressure at that point is 22.4 millimeters of mercury. So that's what we're going to plug in on the previous page. That 22.4 millimeters of mercury for our water vapor pressure. So now to solve for our dry pressure, we're simply going to subtract 22.4 millimeters of mercury from both sides. So the dry pressure, the pressure of the dry gas, is going to be 771 millimeters of mercury minus the 22.4 millimeters of mercury. We subtracted that from both sides. Once we did that, it canceled, or reduced to 0 on this side, and subtracting it from this side, we end up with 748.6 millimeters of mercury. Now remember, we are subtracting, so we have to pay attention to places past the decimal. Since this value right here has one place past the decimal, but this value has no places past the decimal, we go with the least, which means we need to round this to no places past the decimal. So this is going to round to 749 millimeters of mercury.